So if you're willing
to your conscription. So I'm Jeff Bonwick. Just brief background. So the funniest thing, well, yeah. So I'm currently the CTO for the storage group at Sun, and if you know my history at Sun, that's very, very funny. Because I spent the previous 16 years in the software group doing nothing but being pissed off at the storage group. And Jonathan and Greg decided, actually, you kind of have a valid point. Why don't you go fix it? And I was like, oh. So I get to go do that now. Previously, I spent the previous 6 years working on ZFS. I invented the slab allocator before that, and a bunch of the stat tools like kstat and blockstat and things of that nature, as the governor would say.
That's right. Things like that.
Oh, this kind of thing.
That's right. So my name is Bill Moore. Right now I work for Andy Bechtolsheim, designing Sun's next generation server and storage lines. Prior to that, I worked with Jeff. We co-led the ZFS team to hopefully what will turn out to be success. And spent the last 3.5, 4 years doing that. Prior to that, I worked at BitMover for a brief stint, save your tomatoes for later. And prior to that, I helped start a company called 3Part Data, who you may or may not have heard of. It does large-scale enterprise storage. And prior to that, I was at Sun, working on Serengeti, which was their 6,800 line of servers. And again, keep the tomatoes in reserve. You'll have more reason to use them later.
So just a quick sort of calibration thing here. Despite the LISA in the name of the talk, I'm just curious, how many of you folks are actually either full or part-time sysadmins?
Okay, there you go.
Very cool. And how many of you are either full or part-time developers? Okay, and how many of you, if we said vNode, would know what we're talking about?
Are we talking about COSA or?
The other kind of vNode. That's good. And also those kind of.
I bought the 23rd Sun machine ever built.
Nice.
All right, there you go.
Still got it?
Yeah, we still have most of its pieces.
So, the other question is, we can do this either as quickly or as leisurely as y'all are so inclined. Generally, the sort of core material we have here runs about 90 minutes, but for an audience that's more sort of capable and engaged, it tends to go a bit longer. Now, I don't know what folks' time constraints
Do we have another
are,
speaker?
or if we have a specific slot.
All right.
So whatever you can stand. All right, good.
So, get right down to it. Give you an overview of what we're trying to accomplish here with ZFS. A few high-level concepts that we sort of bring to the table here. Number one is the notion of pooled storage. Rather than having the one-to-one mapping as you do today between a file system and a volume manager, or a file system and a disk, basically we want to treat storage more like memory is treated. For example, if you want to add more memory to your server, what do? You turn it off, plug in more DIMMs, bring it back up, and you're good to go. You don't run dim config or create virtual DIMMs that you mount on your applications. So memory is a pooled resource that is managed on behalf of everybody by the operating system.
Add more, life gets better.
Yep. So we wanted to do the same thing for storage that VM did for memory. And so the idea with a pooled storage model is you have a bunch of storage, whether they be disks, storage arrays, whatever, that you add into a common pool that file systems can consume space from as necessary. We'll get more into the particulars of that in a moment. The other thing is as people get more and more data and more devices to deliver that data, we wanted to have not probabilistic, but provable end-to-end data integrity. That is, when you have 1,000 devices with a few petabytes of space, the idea that an error is like this crazy thing that happens every now and then that you want to sweep under the rug, not really the case. You have failures happening all day, every day as part of common operation. So we really wanted to design ZFS with failures as sort of a first-class consideration. There's an executive at Seagate I talked to at one time who was trying to sell us, an ocean liner worth of disks. And he made the statement that there are two kinds of disk drives in this world, those that have failed and those that are about to fail. And coming from, the point of view that he was trying to sell us a bunch of gear, I thought was rather humorous and honest. So the idea that providing integrity of your data involves you sort of looking at it to make sure that everyone along the data path didn't lie to you at some point, which means you got to examine the data. And historically, people have said, nah, you can't do that, too expensive, don't touch the data, a local. So that was true about the last, 15, 20 years ago. But what's changed since then? Well, disk drives have gotten on the order of 10 times faster, memory about 100 times faster, CPUs about 1,000 times faster. So everything's gotten faster, but relative to each other, CPUs are now about 100 times faster relative to disks than they were back then. So for every byte of bandwidth that you have in disk, you have about 100x more CPU than you used to have. So our checksum algorithms run, like gigabytes a second per core, which means you either have an I/O subsystem capable of delivering that, or you wind up spending a small fraction of one core of your many-cored CPU, validating the integrity of your data.
And just briefly, when we talk about end-to-end data integrity, the point we're trying to make is that you have a bunch of sort of spindles in here, and on there you've got individual blocks of data. And the difference between end-to-end and sort of local data integrity is that if you have a checksum sort of associated with this block, and it verifies right here that right now that's the right block and it looks good, that's fine. But then there's this whole journey that it has to make before your app gets its hands on it. And the idea of end-to-end data integrity is that you say, I know up here what I want the checksum to look like, and I go off, ask for the data, get the data back, and then say, is that actually the thing that I look for? Did it survive whatever SAN switches and cables and DMA and drivers and crap that might be inserted between me and the spindle?
And hopefully the answer is yes. And
Or
we'll
if the
get to
answer is
one.
no, hopefully you got a plan B.
That's right. The third point here is that of transactional design. People have been doing this, in databases and other similar type systems for decades now. And why don't we do that with file systems? The idea behind transactional design is everything on disk is always consistent. That, we'll get into how that works later, but when you keep everything in order or consistent on disk, and you don't have temporary windows of vulnerability or moments that you may have to come to clean up later, you can actually remove a lot of constraints on the order in which you do I/O, which allows you to get some really huge performance wins.
But one question, Bill, about this provable end-to-end data integrity thing. How important is this really? I mean, surely all of these storage devices and all this hardware, this stuff is perfect all the time, right? Why do I want to pay for this?
I don't know, maybe you don't. Sorry, so we've actually had this situation come up a number of times.
You're supposed to say Sarbanes-Oxley.
Sarbanes-Oxley. So we actually had this come up. Did I spill something? No.
No. No, it's all fine. You missed.
Yeah, you missed.
You moved.
It's a moving target.
That's right. So we had a developer join the ZFS team. This is a few years ago now, and he comes on board and joins the team, stops by to talk to Jeff and myself. He's like, hey, yeah, I'm on the ZFS team, let's go. It's like, all right, here's a machine, here's a pointer to source code, go build it, install it, play with it, figure out what you want to do. We figured, yeah, it's the last we'll hear of him for about a week. 45 minutes later, he's standing in our door, and he's like, yeah, I'm seeing these checksum errors with ZFS, what's that all about? We're like, wait, you mean you installed your machine, compiled ZFS, and got... He's like, yeah. I'm like, okay. Like, but we're seeing these checksum errors. I know, great. So, guys, first day on the team, already he's hit some catastrophic bug, not really the best foot forward we were hoping to put. So we were in the middle of doing some major surgery on the code at the time, so we're like, all right, let's go take a look. First of all, we do this, and it seems to be kind of randomish, right? We read a block of data, and just doesn't seem quite right, doesn't pass the checksum. So we add a whole bunch of instrumentation to the code. And let's say, all right, now what was the VA that this memory address was like, what was the physical address, what CPU wrote it, what PCI bus did it go over on, all this information, couldn't find any correlation. We're like, all right, fine. Maybe it was good and we corrupted it and then it was bad, so check some of the data before you write it to this, check some of the data after you write it to this, see if it's the same. Well, it's the same answer, so it doesn't look like we did it. So we're like, all right, fine. change the hardware. Must be the hardware. Nope. Swap everything out, still happens. Oh, great. So now we say, well, wonder what happens if you do mirroring. So we do mirroring, and with ZFS, one of the great things about checksums is that you don't have to guess which side of the mirror has the data you want. The answer is, it's the side that has the correct checksum. So we put in 2 mirror disks and start running the test, and it's all okay. Well, what's that about? So now we have both something that we know to be the right answer, something we know to be the wrong answer. So we DD both sections off the disk, compare it, and it always turned out that about 30 to 40 bytes into a sector, there was a run of between 13 to 18 bytes that were just out of the blue, wrong.
And this was particularly spooky because if you ever debugged stuff like this before, what you're expecting to see is there's 64 bytes that are wrong and a 64-byte aligned boundary, and you're like, it's a cache problem. But no, it was just the offset kind of varied, the length kind of varied. Shows bizarre.
And so we said, all right, well, and we fortunately DD'd not only that one sector, but a little bit of area around it. And the bytes that were wrong, we found those bytes at that offset about 8K away. We're like, oh, well, that's interesting. So started doing a bunch of analysis and whatnot, and it turns out there was another group down in Southern California that was having a similar problem. And they actually had like hardware analyzers and stuff that they could use to look at the problem. So they looked at it, because we weren't getting much farther than accurately describing the problem. And as it turns out, the Silicon Image 2114 chip that was on that particular kind of motherboard, look it up, it's a 2114.
3114. 3112 and 3114.
Nope. But anyway.
If it were 2114, I remember because 2112 was a Rush album.
Yeah, sorry. Yeah, but anyway, so there's a Silicon Image something. That's right. So there's a Silicon Image controller, and as it turns out, there was a hardware bug in the logic of the chip. There's actually a race condition that when they had simultaneous transfers going through the chip to like different devices, or I forget how it was, whether it's both ends of their PCI, both the IO side and the PCI side, there would actually be a glitch in their logic that would temporarily select data from the wrong part of the data path and then switch back. And just always momentary, just always shifting a little bit. Turns out that's what the problem was. So now we're pretty mad, right? It's a bug in the damn ASIC. Call up Silicon Image, we're like, damn it, we're seeing this problem. We're like, oh, that's a RADA number 135. We're like, you could have told us. And so they say, oh, don't worry about it. Just install this little bit of code in your BIOS and it'll go away. And as it turns out, it did, but still.
You had a BIOS?
Sorry.
So one of the things that made this difficult, right, is that so the folks who were looking at this at the Southern California site, it had taken them months to get to the point of realizing that they actually had a hardware corruption problem, because the manifestation of it was so just sort of sporadic and random, because as you can imagine, with a normal file system, if you don't have stuff checksum and you get a block of data wrong, if it's user data, you read it in and it's just kind of the wrong data, and that just, that's one of those errors you look at and you're like, that was weird.
Yeah, how did return cap wind up in my password file?
Right. Or if it's the metadata, then you kind of go off into the weeds and you get, free and free frag or some such thing. It must be a UFS bug. Right? So it was just, it's difficult to discern, do I have a software or hardware problem when you don't have any kind of checking on it? So part of what we're trying to do here.
And lastly, before we move on,
I want to go to this page.
Is also, when you have thousands of devices with petabytes worth of data, one of the things that becomes very important is making life easy on the poor little system administrator who's always overworked and underpaid. So one of the things we wanted to do is make really simple administration and not have you walk us through whatever state machine we feel like having you walk through, but just express your intent. We'll take care of the details.
Because you think about how you normally do this kind of stuff, and it's just ridiculously manual. The way you sort of configure volumes by specifying all these little different details about them, and the width at which you want to stripe things, and and then you have to manually edit that ZFS tab and type in all these crazy little things exactly the right way. It's just one little irritation after another, and any one of those things, if you get it wrong, either you get hosed or everything seems fine, except then for some reason there's a power outage or what have you, and then you reboot, and because you didn't edit the appropriate SC files or whatnot, the stuff isn't there. It's like, oh, I forgot to edit my share it, or oh, I forgot to put it in that's VFS tabs, so it would be mounted, or what have you. It's
just, you have a couple overlapping cylinders.
Yeah, just in the overlap, it's wafer thin, but somehow that was the wafer that mattered.
That's right.
Can I ask about something that's not on this slide?
Sure.
You can ask anything you want.
There's like 35 others, so.
I know.
Or 50.
I've always been curious about why distributed file systems, or an idea of this distributed, we have multiple systems and a whole bunch of storage on a bunch of systems, that couldn't be part of this overview as well. In other words, ZFS thinking about a distributed model.
Yep.
Right. So,
which is actually where we're going, because one of the things that's important to people is they want sort of their storage cloud, right? Everything's accessible from everywhere through a single namespace.
Our servers, the drive bays are all filled up.
Yep, exactly. Just want to add something somewhere else, and it's all okay.
And consider it a part of the design,
right.
And yet still be a first order or a first class consideration.
So that sort of stuff actually we have been thinking about long and hard, and it is a hard problem, and we wanted to release a product instead of making you wait 2 more years to have like the product. So right now
we'll get to actually toward the end. There's some stuff that we can say about this, where we talk a little bit about some of the things that we have in the pipeline right now. Okay. Yes.
I know you haven't given the presentation yet, and I haven't read it. but I keep thinking network appliance and how that, some of the things, the snapshots, and how the logging is done. I don't know. Do you have any comparisons that you could mention along the way?
Yeah, we can actually do some as we go along.
Yeah, we don't have any sort of like table things, because I always find those things sort of cheesy, right? Because invariably when someone comes up with a table like that, their thing is full of like green check marks, and everyone else has like red X's scattered through the table. It's like,
right.
Yeah.
And all the benchmark slides, it's like, this file system is the fastest than every benchmark. So basically, every file system is better than every other file system.
That's right.
And so I just kind of, that kind of sort of competitive comparison, I don't find especially illuminating, but we will get into some of the differences between the ZFS structure and Waffle. There are definitely some good ideas in Waffle and what they did in NetApp, but they don't actually scale very well because some of the implementation choices that they made. And one of the things we did in ZFS is to come up with, for example, for snapshots, new algorithms for doing that, such that, like if you look at the NetApp algorithm, it originally limited you to, I think, 20 snapshots, and they've now upped that to 250. No, it was 30, then it was 255.
Yeah.
And 255 sounds like a lot if you're accustomed to 0, right? But then you say, so this is cool. I want to take a snapshot, like once a day, and then 8 months later, you're done, right? It's like you can't take any more snapshots unless you start deleting the old ones. And when you start thinking about some of the ways you want to manage your data over very long periods of time, that's not really cool. If I want to take a snapshot every day or every hour or every minute or every second, I should be able to do that. I should be able to go back, as far back in my history as I want. I shouldn't be forced to delete something if I still have free disk space, right? That's just kind of not okay. So we address that, and we'll get into that in a little more detail.
So what are we really trying to do? Well, put concisely, we're just simply trying to end the suffering. So people are going through an awful lot of pain, probably, and a lot of you guys, having to manage all these increasing terabytes of data on these increasing numbers of devices. And it just really sucks for everyone involved. But whenever you're developing a new system from scratch, everyone loves to say, I know, got the perfect answer, let's rewrite everything from scratch. And really, while sometimes that's fun and entertaining, you really have to figure out why are things the way they are. Everyone who came before you wasn't necessarily an idiot. They may very well have been, but not just because they came before you. So you have to figure out why are things the way they are. It's normally for a very good reason, and sometimes those reasons go away as technology evolves or the capabilities of the systems you use evolve. Sometimes what was a good reason 5 years ago, no longer valid today. So once you figure that out, you get to figure out, well, what constraints are actually fundamental to the problem, and which ones are just historical cruft. And when you get there, it turns out you get to blow away all the assumptions, and you're left with the fundamental problems. And when you use that and you design an integrated system from scratch, you really can put a lot more interesting stuff on the table.
network.
And if you think about the integration part, the thing that I was trying to wound you with, so is that normally in any kind of stack, whether it's hardware or software or what have you, there's some set of interfaces that define the boundaries of whatever that box is that you're talking about. And the interfaces at the top and the bottom of any particular box become fairly well encrusted, and people start to build industries around those. And that's fine, unless it turns out that that interface is in some way limiting, in which case what you really want to be able to do is take, say, a couple of things in the stack that have previously been viewed as separate and say, actually, I want to kind of carve that problem up differently such that there's a new interface between here and here and between there, and these two things that really should have known about each other get to know about each other. And there are cases, and ZFS is one of them, we'll describe in a little detail, where you can get some pretty big wins from that. So, as a way of background, it's helpful to think about why do we have volumes in the first place? Right? After all, in the beginning, there were no volumes. There were just file systems, right? And by definition, and of course you can tell the time frame I'm thinking of by the size on the disk, right? That when you had, say, a 1 gig disk, the purpose of a file system was to, and actually this goes back to like 10 meg and 100 meg disks too. The purpose of a file system, by definition, 640K anyone? But the purpose of a file system was to take a disk of raw blocks and provide structure to it that was useful to software. And so there was, by definition, a one-to-one mapping between the file system and the disk. And in fact, disks were so large compared to the amount of data people had that you would partition the disk and actually have multiple file systems. So it was actually even a one-to-many. But what happened is people started to require more data, is that people wanted that relationship to flip, such that you wanted to say, you know, I'd really like to have more than one disk worth of capacity, but have it look like a single logical entity. So thus volumes were invented. And the idea was to say there's this interface that already exists between a file system and a storage device, and it's the world's simplest imaginable interface. Read a block, write a block. I mean, any protocol, I don't care whether it's, you know, SCSI or ATA, what have you, really, apart from all the like wacky off to the side configuration things and historical cruft and whatnot, all I can do is read and write sectors. That's it. So what then are you going to do if you want to provide something richer? Well, one thing you could do is rewrite file systems from scratch to accommodate the concept of multiple disks. That's actually a very hard thing to do, as it turns out. Harder than I thought. I'm not sure I would have tried if I had known. But the easier thing to do is to insert something in the middle, sort of shim, that has the block device interface up the top and block device interface out the bottom, so that it's completely compatible with all your existing file systems, but can give you a bit more functionality. Right? So a concat, for example, you can actually picture this code in your head. It's such a simple thing, right? To take two 1 gig disks and make a 2 gig concat, all that happens is the volume exports to the file system a 2 gig range of addresses, of LBAs. And an offset comes in and it says, if that address is less than a gig, hand it to this disk. If it's greater than a gig, then subtract 1 gig and hand it to that disk. And you're done. That's what a concat is. You express it in 10 lines of code. A stripe, same idea, except that instead of just having two things side by side, you interleave. So that in addition to having more capacity, you also get more bandwidth because you can bring the data off at the speed of the platters combined rather than just the speed of one or the other. And then the third thing you can do is mirroring, so that you have two copies of the data such that if one of your disks catches fire, you still have a copy that you can get your data from. And in fact, this was a sufficiently good idea, I don't mean to sort of impugn it, that a whole industry grew up around it. So you actually have file system and volume managers sometimes sold together, but also sold separately and reasonably interoperable. And that's good, except that there are some problems in the interface between file systems and volumes, right here, that are very difficult to fix. And in fact, you really can't fix them without going to a somewhat semantically richer model, because when all you have going from file system down to volume is the concept of reading and writing blocks, there's an awful lot of information that gets lost about the relationship between those blocks, which ones are allocated and free, what's your data replication model. The file system can't see information about replication. The storage devices can't see information about semantic structure of the data. That actually costs you a lot.
So let's explore that a little bit more. So, as Jeff was saying, the interface here and necessarily here, is a simple block interface. Write this block, read that block, whatever. So if you want to do something that's semantically meaningful, like renaming a file from one directory to another, what does that involve? It involves writing to the source directory, removing the reference to that file, write to the destination directory, add a reference to the file, write to the file itself to update the C time, and you're done. And then what happens if you lose power? Well, hopefully you can come back with our pal, FSCK, and find the mess and clean it up and say, oh, well, this file is like in both directories. Wonder if it's a hard link or whether that's the way to, or here's an unreferenced inode. Let's go put it in lost and found. That's where everybody would like for.
Because think about it, right? I mean, logically, you have some file, and you have two directories, and they both want to have links to that file, right? Or
Well,
actually,
only one of them does.
only one of them does.
You want to move it.
Is there an eraser?
There is.
This is not tape, is it? Yes, it is. Of course it is. So what you want to
It'll
do
cost you too.
is you want to be able to say, you know, the timestamp on this is, 7, and there's a name in here, foo, and you want to change that name to bar over here, so you want to do a rename. And what you want to do is take foo out of this directory, take this link away, add a new link over here, change the timestamp from 7 to 13 or whatever it is. And so there's several different disk writes that have to happen. There's whatever block of the directory structure that this lives in, there's some other block or more than one potentially that this lives in. There's the inode for this file. All this stuff has to get updated. And if you were to lose power in the middle, say after removing the name foo and removing this hard link, but before creating that hard link, now I have no way to discover this file at all. So when FSCK runs and says, I just put this file in lost and found, that's because it discovered that inode number, whatever this is, has a non-zero link count, yet nothing is linked to it. So it doesn't know what to call it. So it puts it just in lost and found and figures, you're smart, you figure it out. Which is not bad when there's one file there. It's a little less good when there's, say, 10 million files there.
That's right, and of course people realize this, and that's where you have journaling, which doesn't really fundamentally solve the problem, but is an acceptable workaround. So the way journaling works is you have the journal and you write in your diary saying, I'm going to rename this file from here to here. Then you go and do all these things, and if you lose power, the fundamental mode of consistency is really still the same. In other words, FSCK, but now this journal tells FSCK exactly where to look to clean up the little mess that might be there. And that's exactly what happens. File is finished being renamed, and you're done. The problem with that is it adds even more constraints on the problem. So you already had this constrained order in which you had to go rename the file. In addition to that, you have to synchronously write to the journal, go do the same stuff you had to do anyway, and then sometime later write in the journal that you've done. So this adds more work for you to do, synchronous work, which really sucks.
Yeah, and so partly it's slow, and partly it's complex, because journaling invariably is bolted onto the side of a file system. You start with a file system that wasn't designed to handle this, and then you kind of glue onto the side this thing that keeps track of all the stuff that's in flight. And it's really, journaling is actually sort of a glorified term. FSCK accelerator would probably be a better term for it.
Journaling's the right term. What you want to do
Well,
is a transaction-based journal.
One, indeed. Indeed one does.
Like all the database people figured out in the 70s.
Yeah, how about that? Indeed.
That was
And we
actually,
should
so
learn
this is,
something
I probably shouldn't tell you this, but this is one of my interview questions. When you get somebody who's coming to interview at Sun, and this was especially true like around 2000 when, Linux was one of those words that you would just say it and it was, that was the answer to, what was your question? Linux is the answer, right? And so one of the questions I had was, why would you want to come to some Linux startup and work on problems that Sun solved in 1985 when you could come to Sun and work on problems that IBM solved in 1970? Because all this stuff is cyclical in the end.
Yeah, so the volume manager doesn't have a much better time of things. He has no idea what the file system's up to. Renaming files, what's that? All I see is a bunch of writes coming at me. And for all he knows, those writes are coming in that order for a very particular reason. Because, well, they are. And as much as a volume manager would like to say, you know what, if I were to reorder these writes around a little bit, I can make it go a lot faster. He can't, because there's semantic happenings in the file system that depend on that, and you're pretty much stumped. All he can do is say, all right, single-minded, you have 2 disks, gotta be the same. 2 disks, gotta be the same. Synchronously write everything to each side, done. Problem is, again, if you lost power, if you lose power, well, which side of the mirror is right again? Not really sure. If you had a single copy and you want to make it mirrored, well, we'll just copy everything over. It doesn't matter if the file system's 5% full. Copy one device to the other. And it's just a lot of constraints on the problem just because he is kept in the dark on what the file system's up to. So as Jeff was saying, a lot of times where you can get a lot of benefit is to do what we took the opportunity in ZFS to do, which is refactor the problem. So coming into the top here on both sides is your POSIX file system API. Read, write, open, close, rename, unlink, all your favorite system calls are there. Coming down here to disks, well, you're not going to change your disk industry so much, so read a block, write a block, that's pretty much what you got to work with. All the stuff in the middle, though, is fungible. So what we did was we sort of started in the middle and said, all right, what's the abstraction we'd really like to work with? And started with what's called the DMU, or Data Management Unit, which doesn't know anything about files or directories. It knows nothing about nothing. All it knows is about objects and transactions on those objects. So the API it exports is a transactional object interface. Given a transactional object store, writing a file system, not as hard as it might otherwise have been. So the ZPL, while it's kind of snarly because it has to interface into the ugly parts of the OS, conceptually, it's a very simple thing. So for example, say like that nice rename call comes in again. What do? Well, pretty straightforward. You create a transaction. As part of this transaction, you say, I want to update the source directory to no longer contain a reference to this file. I want to update the destination directory to now contain a reference to this file. And I want to update the inode of the file to have a new C time to show that it was renamed. And I want to close that transaction. I've now described an atomic unit of work that either has to succeed or fail as a whole to keep the file system in a consistent state. Give that down to the DMU, and it's like, all right, got you, boss. One transaction, modification to these 3 objects, no problem. So then the DMU, because that's really a microscopic amount of work, really wants something a little more meatier to do. So he bundles things up together in something that we call, in a fit of creativity, a transaction group, which again has the same semantics as a transaction in that it's all or nothing, except instead of being one, it's several, and we'll get into why that's important later. But again, all or nothing, and because of this, because we're transactionally describing what you're doing to your file system, there's really no journal needed. Everything always remains consistent on disk. And again, we'll get into why later. Now you have a semantically very rich description of the changes going on to your file system. Now that you have that, when you go to what we call the storage pool allocator, or SPA, that handles the rating and the disks and the actual physical I/O, you now no longer have to guess what's that crazy file system up to. You now know exactly what he's up to. So now, if you want to reorder a bunch of I/Os, well, you can do that as long as you obey the transactional constraints laid out to you by the system calls that came in. So you can reschedule, aggregate, issue I/O however you want. Again, you have the information in hand. You know what parts of the disk are used, what parts are free. You don't wind up resyncing non-data. And because you can do all of these optimizations, you can run at or near platter speed a large portion of the time.
And one of the things that I personally found surprising about this is that you would think that if you go from a model where you can pretty much update any block anytime to a model where you're putting constraints on the definition of what is a transaction and what is a transaction group and rigidly defining these boundaries, you look at that and you think, well, fundamentally, because that is a more constrained description, it must be harder to optimize. It must make it go slower. And yet it turns out that in fact, because you know what the constraints are and you don't have to guess about a whole bunch of other things down at a lower layer, you can actually get huge wins because all the places where a volume manager has to assume things about when it needs to keep the sides in sync, when in fact it doesn't actually matter, all those constraints go away. And what we inherit in exchange is a much more, a much smaller set of constraints on how to do a giant bucket of I/O, and basically within that giant bucket, we can reorder things any way we want, we can schedule, we can aggregate, tear things apart, defer them, put one thing ahead of another because of priority considerations. All that stuff just works because we know we actually have all the dependency information down at that level, which things can be ordered ahead of which other things. And apart from that set of constraints, do whatever you want.
Can you say datagrams instead of switched virtual circuits?
Datagrams instead of virtual circuits.
That's right.
Yes, I can.
Yeah, so this sort of covers things
Yeah, I do.
for a single file system, and let's see how sort of the problem looks with multiple file systems involved. So as we mentioned before, the current way of thinking about the problem typically is you have a file system, maybe a volume manager, maybe not, and some set of disks. But the fundamental notion is that a file system is tied to certain very specific, can put your finger on them physical resources.
And if you remember nothing else, that's the presentation. The old abstraction is a virtual disk. The new abstraction is malloc and free. That's kind of the heart of everything that we're doing here. It's the difference between virtual addressing and virtual disks. It's the difference between VAs and overlays.
Do I get the rest of Multics too?
Well,
That's right, see,
Like I
solving
said.
the problems of the 70s, why wouldn't you want to work for Sun?
right, just like why was there,
Resolving.
just like why was there a bubble in the 90s? Because everybody who was alive in the 20s is dead.
That's right. Indeed.
So what do the inodes look like now?
What do the inodes look like? In what sense do you mean?
Down at the disk level?
So, actually, well,
Everything is no longer in sort of a fixed, well-known location. The
Right.
way it works is kind of like, if Firefox wants more memory or ZFS wants another inode, it says, please, may I have the place to put that data structure or that inode on disk? The storage pool says, yes, you may, right here, and you write your inode there.
So it's no longer an inode, presumably, it's
It's a
something
Z-node.
that's hidden, it's a C node under a V node, presumably.
yeah, and so in some sense, the way to think about the question is that right now, when you create a file system, it's a meaningful thing to say, how big is the file system? And the answer is, well, it's as big as whatever the underlying volume is, because it's
How
basically
many inodes do you
a
have?
virtual device that has a certain size, and based on that size, you say how many inodes you pre-allocate and things
But
like
first, how many cylinder groups do you have?
that.
Super blocks.
Oh,
Right. Whereas if I were to ask you, how big is Firefox? Now, that's a bad example. It's a pig. It's a gigabyte. It's all right. But ignoring the fact that it sort of like leaks like a sieve and it consumes obscene amounts of heat. How big is Firefox? Well, it's basically size 0 when it starts, and then it brings in its 295 shared libraries, and then it gets to a certain size, and then it allocates and frees things, or allocates things anyway. And so its size varies over time based on what the particular load looks like for that application. So Firefox is not, you don't create it and sort of associate it with the DIM and say Firefox is a 200 meg application. It's just an application, and as it needs things, it gets them. As it's done with them, it gives them back.
It's as big as it needs to be.
so a better question really is, what is your block level, and then what is your total system level overhead? Because now, of course, you've got linked list up and down the hierarchy, blah, blah, blah. So you're going to be just like an IP packet, losing some amount of
So the answer is that
granularity.
in all the analysis that we've done, in every file system we've looked at, it's been between 1% and 2% overhead
That's at the block level or at the file
at
system?
the block level.
Okay,
So
block
for
level.
all of your files, in other words, if you have 100 megabytes of data, typically you'll have a megabyte and a half of metadata associated with that 100 megabytes of data.
So
And we
at
actually,
the block level, you're burning about,
Percent.
yeah, about 32 bytes.
And ZFS is no exception to that?
I was answering the question for ZFS.
Yeah.
yeah. And actually, if you compare it to other file systems, they turn out to be about the same once they're populated. So the only difference really is that we allocate metadata on the fly. Others tend to, pre-allocate, right? So
Probably what's happening is that the pre-allocations are wasting a lot of space, and you're not wasting space pre-allocating, you just got all your doubly linked lists and stuff like that spread out all over the place.
yeah, we'll actually, so for those who are so inclined, we'll actually get into some of the data structures later, because that's actually kind of interesting. In fact, one of the things, I shouldn't do this because it's a tangent, but should I put up the block pointers? Should I talk about block pointers?
Oh, wait.
All right, we'll get to that.
We can imagine some
Okay.
of us.
Do you still have the ability to take a volume, fill it with a certain amount of data? I know this is on the volume side terminology, but then move that volume somewhere independent of the rest of your storage. But it looks like if you have this one giant pool, you don't have the flexibility of just putting some data on a drive, moving it somewhere.
Right, so there are two options. So in case anyone can hear it, the question was basically, do you have the ability to move volumes, from one place to another?
Move data in sets.
Move data in
Yeah.
sets as opposed to, the
So
pool
before we
storage.
answer that, let's finish sort of what we were saying here first. Sorry. So typically, if you have a file system associated with a volume or set of disks, if, say, one file system is full, the others are empty, well, sorry, you fundamentally have fragmented or stranded your storage. Nothing anybody can do to help. Similarly, if this guy needs a lot of bandwidth, those two are picking their nose, well, again, sorry, nothing you can do to help. So in a storage pool, it's, again, as Jeff is about to get into, you have a pool, bunch of disks in there, and now there's no longer this one-to-one correlation. You can have as many file systems as you want, and how much space do they have? Well, as much space as is not yet consumed. How much bandwidth do they have? Well, they have the bandwidth of all devices available to them, subject to whatever resource constraints you put on top of it. Now, back to your question, in terms of, well, all right, but do I lose then flexibility for pushing my bits around? So you can still take devices, move them somewhere else, add them to the pool, whatever, and the pool will grow and when they shrink as appropriate. The other thing you can do now is because these file systems are no longer tied to physical blocks, is you can move them around as logical entities as well, no longer necessarily physical entities. And there are some slides later on that'll get into that. It's a ZFS send receive is what we'll be getting into.
The other thing we should mention too is just that if for whatever reason you want to have more than one storage pool, you can certainly do that. And in fact, one of the things that we're planning to do for when ZFS becomes the root file system, so we have a project way to do that, is that in general you're probably going to want your root pool to be different from your data pool. Because
Physically separated.
Physically separate, because you don't want the machine's personality tied up with your data. You want the data to be portable, and not just portable in the sense of moving it from, one AMD box to another, but if you want to move from AMD to Spark or Spark to Power or whatever, you should be able to do that and not have to worry about endianness and crap like that, and we actually took care of all that stuff too.
And it slices and dices.
So just get Julian fried.
So how do we do transactions? So this part you'll recognize if you ever studied databases. It goes back to it goes back a long ways. How does one update a tree atomically? And it's actually kind of a cool thing. So normally, if you had a file, so every file system, just to, by way of background here, every file system in the end is a tree of some kind. It may have various little substructures along the way, but in the end, there's some block that is the master of them all. One block to rule them all, one block to find them, one block to bring them all on, to spin and bind them, in the land of storage where the vendors lie. So what we have to do is say, all right, so in a traditional file system, if I wanted to modify those two blocks, I would modify them in place, and that's a straightforward thing to do. But we want to have copy on write so that we can do both guarantee transactional integrity and also the ability to do snapshots. So instead of modifying these two blocks, we're going to allocate two new blocks, shown in green, and go ahead and write the content of those. Now, at this point in time, in stage 2 here, suppose we've written the content of those green blocks, and you lose power. Okay, so you come back up, and you start at the blue block at the top, and everything that's visible to you in that tree is the blue stuff. You don't actually see the green stuff, because those green blocks, as you'll notice, there's no arrows pointing to them. They're not linked into anything yet. They're basically free space that happens to have had content written to it, but that content hasn't been committed yet, so nothing points to it. All those, the blue blocks underneath, unmodified, unharmed, still intact. Now, we want to make this block up here point to those modified green blocks, but again, you don't want to do it to the existing indirect block. You want to modify it later, so you allocate a new block, make pointers to the new data, same thing up the tree, and now we've gotten all the way to the top, and the same rule is true, that if I were to lose power at this point in time, all I've done is modify what's in green. That's all currently considered free space. All the arrows discoverable from the top point to blue stuff that is unharmed. finally, the coup de grace, we modify what we call the Uber block. It's the block that sits above all the others. And this is a single atomic disk write. We actually have some code to put the Uber blocks in a ring buffer in case the disk actually doesn't do writes atomically, although they generally tend to, but we don't trust them. So you rewrite the Uber block, we make that logically atomic so that you go from the blue view of the world to the green view, which is a hybrid of things you changed with things the way they used to be. And there's no point, there's no window anywhere in here where you're at some kind of indeterminate state on disk. That's why there is no FSCK, there's no journal, there's no anything like that in ZFS, because there's no matter when you lose power, there's no point at which you're in an inconsistent state.
Right, and this bring up, I think, one of your points that, well, databases have been doing this for what, 3-4 decades now, and yep, this is the classic phase tree approach, and well, you're right, at least a few decades old.
But
what happens if you lose power when the head is actually writing to the disk media?
So we actually have several.
To the upper block.
Right.
Yep.
So it's actually a multi-phase commit. Is it 2 or 3 phase? I can never remember.
It has to be 3.
Yeah. So
what we actually have is there is an array of Uber blocks.
and before you get into
The array
Uber
buffer.
blocks, there's actually more than one array of Uber blocks. On every device, if you think of a device as a sort of from block 0 to block infinity, we actually have 2 labels at the front of the disk and 2 labels at the back of the disk on every disk. As part of this label, each one of these labels, so there's 4 of them total, is this ring of Uber blocks that Jeff was talking about.
Right. And so
For devices like flash memory or flash thing where if you keep writing the same area of the disk, it wears it out, is this ring buffer large enough that it's going to be, on average, used the same as the data blocks?
Yes, it's one of the reasons we made it rather wide range is for exactly that reason. But as one of the things the hardware guys are doing the flash chips is they introduce hardware wear leveling into the actual chips themselves. So it's becoming less and less of a problem, even though we tried to solve the problem.
Well, you have to solve it at your level such that no matter what happens at the disk level,
Right.
you don't block and cause us to start losing nines.
right.
Yep.
So we have this array.
I can't get the
What
Linux
happens is-
people to understand that, by the
Yeah.
way.
So you have, let's say that the last time you successfully wrote a transaction group was transaction group 37, because that's our standard number for transaction group for some reason. And so that's on disk, that's stable, that's cool. And what's sitting here, and maybe this is actually a bad example because the array is bigger than this, but let's pretend that 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8's a nice number because it's a power of 2. So 8 away from 37, right, the last time, since this wraps, right, the last thing that would have been here would have been 29, right? So what's sitting over here is the Uber block for transaction group 30, okay? And now we come along and we say, we want to write out the Uber block for transaction group 38. So we start writing out the contents of 38, and then the disk dies, or lose power, some horrible thing happens. So now we've got this half-baked block. It's partly 38, it's partly 30.
It's half-baked because, of course, the checksum's wrong.
Exactly. So the way we discern this is that we have a SHA-256 checksum on every one of the Uber blocks. And what happens when we bring up a pool and open it for the first time is we read in all the Uber blocks and we say, of those that have a valid SHA-256 checksum, which one has the highest transaction group number? So 37 is going to pass as the candidate Uber block. 38, because we didn't actually successfully write all the bits out, is not going to pass. We won't use him. And so we'll pick up at 37, which is exactly what you want to do, because until the Uber block is successfully written to disk, that transaction group is not considered to have been committed.
Now, using a SHA-256, you have 64 bytes of SHA sum. How many bytes are you using for the Uber block counting number?
8 bytes. So it's a 64-bit number.
Right, so there are 2 to the 64th transaction groups before a
Can't
rule
write
becomes unusable. Yeah. So that's a while.
And if you're pushing one out every microsecond, you have a few centuries.
Yeah, that's.
It's actually, it's better than that. You
So it's
basically,
not our problem.
It's actually, if you push out one a second, if you push out one a second, you have until longer than the sun goes supernova.
So we'll do one a microsecond.
Okay then.
Yeah, but you have to convert the mass of the galaxy into
But you
states changes.
You have an Uber block resetting procedure,
Oh, do I have a
right?
slide for you?
You have a little Uber block resetting routine, don't you? I want to just set it back to 0 so I can just.
That's using baryons, not leptons.
So every time you do a write to disk,
Ah,
create
right.
this whole
No,
secondary.
no, because if we did this, every time we did a write to disk, it would just suck, right? Because it would be so slow.
Well,
So-
also, you
It's
knew you
slower
would
than
get
Dennis
one
office.
little linked list there, or block of data there would get worn out of it.
Right, so there's a couple things. So first of all,
What kind of performance degradation are you realizing when turning on the snapshot feature?
none actually, because when you allocate, so when you, actually I'll talk about snapshots on the next slide if that's all right. But, so if you were to, let's just sort of go back to the first principle. Imagine, if you will, that every single time someone does a transaction, a single write system call, that we went through this entire dance. Okay, that would suck, because it would mean that instead of writing these two blocks, we'd have to get these blocks written, and of course, it's not just writing them, but you also have to allocate them and find out what address did we select for that. And that becomes a factor in deciding what to write out to this block, because the addresses of those blocks are part of this block, and so on up the tree. And so you'd have, potentially, depending on how you coded it, either a bunch of IOs with serial dependencies, or you'd have a bunch of IOs such that any one of them failed, you'd have no good way of really recovering other than kind of throwing everything out and starting from scratch. And it would just be unspeakably slow. So what we do in practice is, this is why we have transaction groups. So you bundle up multiple transactions into a single transaction group. So that, two things. One is that this tree, first of all, it's not actually binary. We've drawn it that way just so that it sort of fits on the slide. It's actually much wider than that and fairly flat. Number two, this describes the structure of each individual object, not the directory structure. So in other words, if you have a directory structure that's 1,000 deep, that doesn't mean that your tree is 1,000 deep, right? Because the inodes are basically flat, and then these are just the indirect blocks within each individual object. So what we do is we accumulate a bunch of things in a transaction group, and what typically happens is that if you're writing, say, a bunch of, well, if you're writing a bunch of large files, the overhead of this doesn't matter, because most of your I/O is in doing data blocks, and then the indirect blocks are a tiny fraction of a % of that. Just like the other case that comes up commonly is that you create a file, and that file is, say, 37K, right? And so what we'll allocate, which because we have variable block size, is exactly 37K. The block size goes from 512 up to currently 128K. So the typical file will actually be, and the other thing is that files normally, unless you are a database, you typically don't do record structured access. You actually just create the file, write the contents, close it, and then you're done, right?
Or append to it.
Or append to it. And so what actually happens is you create the file as a single block, and then there's a bunch of files you created. Those have sequential zenode numbers, so they're in the same block. And you have a lot of sort of coalescing of IOs, such that what we typically see when we push out a transaction group on a server is something like, you'll have maybe 10,000 data blocks being written out, about 100 indirects at level 1, maybe a dozen at level 2, and a couple of stragglers after that, plus the user block update. So
Yeah.
almost all the data is actually user data.
And this goes back to what I was saying before, is on average, the ZFS metadata is about 1 to 2% of all your data. So for any given amount of data that you write, you're gonna have to write about 1 or 2% of metadata to reference that. So in any given group of IO, 1 to 2% of the IO you're doing is for ZFS metadata.
But that kind of wasn't my question,
Oh.
which was
It's a long answer for not being your question.
the Uber block was going to be rewritten
Yes.
every time one of these group transactions happen,
Right.
Mhm.
right? And so and the Uber block is going to be spread out over that ring structure there,
Right.
which is a physical part of your hard disk.
Yep.
Right.
And so the number of writes to the Uber block ring as opposed to any individual block on the disk is gonna be much higher, right?
Right, so we typically push out a transaction group about once every 5 seconds. It can be a little more frequent if you have, I mean, basically the two things that determine it are, one, is that we don't want your data to become more than 5 seconds old. We don't want to have the case that we have in a lot of existing file systems where you modify a page and it sits there dirty for a day and you lose power and the change still hasn't made it to
I
disk.
understand that,
Right.
but
So
an Uber block.
that
compared
really
to-
happens.
But the number of times you update
Oh,
an
sync
Uber.
every 30 seconds.
You must type a lot.
No,
I know, say,
almost every Unix box is sync every 30 seconds.
not sync all the data, you can't anymore. It's too big. They used to be that way, but typically now what you have is you look at the VM system and between a combination of paging considerations and NUMA considerations, there's, well, even this kind of takes a bit afield, but.
Okay, so
there's-
NUMA, by the time you're going to NUMA, you mean big systems aren't doing this at this point?
Yeah.
Okay.
Which is where you're most unhappy if it doesn't happen. So, sorry.
So,
Were we-
yeah, so the number of times you're updating this Uber
Oh,
file
right, so
structure
we're
compared to a conventional file system where you're only updating the superblock once in a blue moon is much higher, right?
Not really.
Well, actually, because you're updating the super block a lot more often than that,
Yep.
because remember, it has your cylinder group summary information and all this other stuff that also has to be kept consistent. So your super blocks are actually written somewhat frequently, and what we do is two things. Number one is we have, many different places we can write it, but also if you have more than one device in your storage pool, we only write Uber blocks to the devices that we allocated data on, so not every device is involved in every Uber block update.
Are those duplicates of the labels so they're all kept consistent?
Yes, and
Yeah.
this is how we do the
Actually, that's what the
two-phase
two-phase update,
commit.
yeah.
Is you write the Uber block here, you write the Uber block here, you write the Uber block here, well actually no, sorry. Let me erase that. So you write the Uber block here, and you write it here, and then you're done. So at any point in time, you have multiple potential copies. All you need to do is be able to find one of them, and you're good to go. And if something fails before you get them all out, and the ones that you already wrote out somehow get scrogged, well, you haven't made any further changes, so, the blue state of the world is still a perfectly valid state of the world.
So in rough numbers, so the Uber block updates happen approximately every 5 seconds, okay? We have in this ring buffer, if I remember correctly, 128 Uber blocks. So that means the ring buffer is on the order of, 640 seconds, which is about, 10 minutes. And if you have multiple devices, it's sort of cycling around on that. So in fact, even though...
And we don't push out an Uber block if you haven't made changes to the file system.
So
Right.
when step 4 happens, one Uber block gets written, 5 seconds later, that gets copied, or that'll
Yeah, so-
get copied to
so-
all the
So right
labels.
now, I write this Uber
No.
block.
That's
5
part of
seconds later,
four,
I write
all
that
four are
one.
written.
5
four-
seconds later, I write that one.
Okay.
And then it's a ring buffer.
Right, I got that. It was
Times
talking about
4,
the
one for
label.
each label.
Oh, right,
Yeah.
yeah.
Okay.
All the labels are identical.
So it writes it, but now having it at the beginning and the end, that means a big seek, or is that really kind of a minor?
It doesn't
Well,
even
again,
see.
it's a big seek, which on a typical drive for a full bore seek is going to be on the order of 8-9 milliseconds on your, medium class drives, and you do it once every 5 seconds. Not that big of a deal.
Unless you're writing a whole ton of data. And then all of a sudden.
No,
Okay,
there's
so
never a
that's
ton
what
of
I do.
data at this level.
Right, but
Right.
if you're running enough data to trigger another Uber block update because
Right,
you're.
then it's going to take you a non-trivial amount of time to get that data out. So again, it's one full bore seek for however long it takes you to write out that big gulp of data. Which again, is going to be on the order of seconds, not microseconds.
Okay.
And you had a question back there? Yes? No? Oh, okay.
Okay, so bonus for this model is that you get snapshots basically for free. So one of the things that we didn't talk about on this page is when you go from step 3 to step 4, what happens to these blue blocks over here? If the slides are literally correct, then we leak those blue blocks. And that either means that we have a horrible leak in our file system, or it means we have a garbage collector, or it means that the slides are a little bit inaccurate. And it's the latter. So in truth, this tree encompasses not only all the user data, but also all of our metadata, including the descriptions of which blocks are considered allocated, which are considered free. So in a fully fleshed out tree, what you would actually have is not just the mods to user data, but for example, for these 4 green blocks, you would have the mods to our space maps indicating that those 4 blocks had been allocated and these 4 blue blocks had been free. That's all part of the tree that gets updated when we update the user block.
And this again goes back to another reason for the transaction groups, which is, remember, the transaction groups are still atomic. They have to succeed or fail as a whole. So what happens is, as we're going through figuring out what blocks can be allocated, need to be allocated and freed as part of a given transaction, we might make modifications to our metadata, our space maps, transactionally as well, and add those transactions into the transaction group, so that the whole description of not only what changes the user is making to their file system, but also the changes we're making to the storage pool to accomplish that, all succeed or fail as an atomic group.
So your snapshots aren't free, you're just paying the cost of an upgrade. That's basically what it is. It's not that they're free.
Well, so what I mean by free is that it's free in the sense that if you decide to take a snapshot as part of a given transaction group, then the bookkeeping to say that those blue blocks were free doesn't actually have to happen, because all you do is actually allocate 1 block to keep track of the route, and you're done.
So that lockup
Right,
one
but
of
you
your,
aren't paying for it.
It's
But by paying for it, I mean the amount of I/O you
I
have to do.
understand that,
Okay.
but see, if you're differentiating from NetApp,
Yeah.
I understand it's different because you're copying on write on everything.
Right.
But it's the same concept in terms of the snapshot exists.
Oh, it's the same concept, absolutely. The thing that's the key
It's
difference
not like
is that.
snapshots are free and they're not with the NetApp or they're not with other things.
Oh, sorry. No, well, actually, there is a difference, right? Which is that in the case of NetApp, there's a for each block, there's a bitmap describing whether it is or is not allocated as part of that snapshot number, right? That's why they have a fixed number. And when you take a snapshot, there's partly getting a new route, but there's also updating the allocation state to indicate what things are live in which snapshots. And that limits you to how many snapshots you can have. By contrast, in ZFS, what we actually have in each block pointer, so a typical file system, and this is why I was so excited about putting up a block pointer, which you wouldn't think is all that exciting. So normally, what is a block pointer in a file system? It's a 32-bit or 64-bit integer describing an LBA where you go off and find the block, right? In ZFS, we have what we call luxury class block pointers because we're a little bit embarrassed about how obscene these things are. So a block pointer for us actually consists of, first of all, it's 128 bytes, not bits, bytes. So it's a quarter of a sector. Okay, this is the Queen Elizabeth of block pointers. So QE2, not the Queen of England. No offense. So why on earth would we have a quarter sector thing? Well, it turns out that first of all, because we have variable block size, the space we actually consume on block pointers is negligible. Even when you have a ton of data, almost all of it is either in small files, to which there's exactly 1 block pointer, or it's in large files, in which case, relative to a 128K block, a 128-byte block pointer is only 1/1000th of the space, so it's still no big deal. In exchange, though, we get something very powerful, which is all kinds of yummy semantic information that's hidden behind this lectern. All right, fine. I'll do it over here. We can put all kinds of yummy semantic information in the block pointer. So, for example, we have a 128-bit, that's bitmap byte, what we call data virtual address, describing on what device and at what offset can I find the data described by this block. That's what a typical file system block pointer provides for you.
that implies that there's a table somewhere that says, for this device, this is its unique identifier?
No, so it's just literally, the DVA is what we call a virtual device and an offset. And the virtual device typically is actually, so think of the single copy case as the simplest. You have a single disk and picture a pool of 10 disks. each disk has a number, 0 through 9, and this tells you if the data was on, say, disk 5 at offset 397, then 5, 397 would be our description of where to go locate it. As opposed to the way a normal stripe is constructed, which is you have 10 disks, and you say, oh, if you want to be block 397, that means, you know, offset 39 on disk 7, because it's div 10 mod 10.
So that means,
which means you can't really grow or shrink the stripe very easily.
So that means that your inode, in a sense, can point to data on a different device.
Yeah.
Absolutely.
That's
absolutely
the
can.
whole point.
Yep. So you
It's
actually
one of the
have
points.
Yeah.
one of the points. So there's a DVA, and in fact, as we'll explain for later, there are actually 3 of them, so that we can have copies of the data above and beyond whatever you're doing for mirroring. There are various properties that we have in here. The thing that is relevant to snapshots is we have what we call the birth time, which is when did we take the particular snapshot. And what you want to do is you want to draw the dead list picture.
So the birth isn't a timestamp, it's a reference into...
Exactly. So every pool begins life at transaction group 4. It doesn't matter why, but, and then so you can have up to 2 to the 64th minus 4 transaction groups over the life of the pool. And basically each time you do a new transaction group, that just increments by 1. So we're not sensitive to, you know, somebody setting the data on the machine. That would be kind of nasty.
When you keep a snapshot, does that tie up one of the blocks in your Uber block ring?
No, we actually put that somewhere else.
Well, it does for a while. Until you shuffle it out of there, presumably. Because it's behind the sweep of the continual moving.
Well, so
It's there until the sweep goes around the 128.
No, it's actually, it's the, just implementation detail-wise, it's just slightly different from that, such that basically when we take a snapshot, we don't actually snapshot the entire pool, you snapshot one of the data sets within it, and each data set has its own root block. So
we're further down in the structure.
So it's actually a little bit further down the tree, right? In principle, we could take whole pool snapshots too. It's just that for the administrative model, it turns out that doing things on data set granularity is a little bit friendlier. So what Bill is drawing up over here is a picture of what does it look like when you have a bunch of blocks in a tree and they've all been born at different times because a file's been updated at different times in its history, and you now want to determine for a snapshot which blocks are part of it, which blocks aren't. And in particular, when you decide that you want to free a block, if a block is currently part of your live file system, but it's also potentially part of some number of snapshots, since we don't have a bitmap saying which snapshot something's part of, we have to have some way of determining, when you say, I'm done with this block, when is it truly done? When is the last reference gone away? And that's actually a harder problem than you might think, because you might think, well, okay, if a block is going to be part of multiple snapshots, just put a reference count on it, right? And then, you know, up the reference count when you take a snapshot, decrease it when you delete the snapshot, and when the reference count goes to 0, you free the block. The problem with that is that in order to do it that way, we would have to, every time we took a snapshot, then say, create this whole map of reference counts, and go increment all these things, and it would take forever. And we wanted snapshots to be constant time.
Right, so the way this kind of works is you have a indirect block tree, again, for simplicity, and because I'm horrible at drawing, it's only a 4-wide tree. But imagine that the current Uber block is, say, transaction group 80, so virtual time 80. What this means is that in ZFS, because every time you rewrite a block, you necessarily have to rewrite all its parents because it's copy and write. They're in a new location. You got to point to the new location, so you got to rewrite its ancestry. So anytime you rewrite a block, all of its parents are going to be rewritten as part of the same transaction group. So what this means is that for any given parent, its transaction group number represents the newest block anywhere underneath it. So in the case of this guy here, transaction group 80, that means somebody under him somewhere was at least transaction group 80, otherwise he would have never had to be written. And you know, maybe there's a combination of 10, 80, 71, 40, whatever, and so on. I've sort of drawn a few here. And then again for this guy, because he's say transaction group 10, that means the newest guy underneath him was in transaction group 10. Similarly for any of these other blocks, the same sort of logic applies. So the way we wind up doing snapshots actually takes this into account and becomes very, very interesting. So at some point you have time 0, file system is empty. Sometime later you have a snapshot, say that was in transaction group 37. Sometime later you have another snapshot, say that was in time 70. And right now you have your live file system, that's transaction group 80. So what happens is every time we go to free a block, the way NetApp does is they essentially have a bitmap to say, is this block unique to this snapshot? If it is, wind up freeing it. The way we do it is all based on this birth time information that we keep in our luxury class block pointers here. So for example, say like we're freeing a block that's part of this file system, and the birth time of that block, when that block was written, is say 75. So we ask the question, is that birth time of that block older than the most current snapshot? In this case 70. The answer is, well, no, it's newer than that snapshot. So you know that that block, born in time 75, isn't referenced by this snapshot or anyone before it. So as a result, when you want to free it, well, it's free. It can just go to the graveyard, the great big bucket in the sky, doesn't matter. However, say like you're freeing another block in here that was born in time, say 40. So then you ask the same question, well, it is older than this. So now you know that either this snapshot or one of his pals before him references that block. So you can't really free it because someone needs it. So what do you do with it? Well, you can't go and free it. So you got to do something with it. So we add it to a data structure here that we call a dead list. And the dead list consists of it's basically just a whole bunch of block pointers that are blocks that would otherwise have been freed, but that you can't free because someone's referencing them. So it goes on this guy's dead list, and life goes on. So you're going to have a whole bunch. If you're churning a lot of your data, you'll have a lot on this dead list. If you're not churning your data, it'll be pretty small.
So if you had a block that was 10, it would go on 37 and 70's dead list?
No, so let's do those two examples. So we got, say, one that's born here in 40 and one that's born in 10, dead list of 2. Now, you want to go delete this snapshot, say, done using it, tired of it, been around too long. Now what you do is you don't have to traverse the entire snapshot to figure what you can free. The only things you have to consider are what's on this dead list, because you've stopped referencing them, and for everything on the dead list, you then ask that same question. Was it born in 37 or newer? So in the case of this guy in 40, the answer is no. I can actually free him now. For this guy in group 10, now this guy is referencing him, so I got to put it on his dead list, and so on and so forth. So you build up this dead list, pretty simple operation, and then when you delete a snapshot, all you have to do is very rapidly traverse this dead list, very dense, very tight data structure. Again, asking the same question, either freeing the block or putting it on his predecessor's dead list. So that's how we get around the need for having bitmaps that account precisely for every snapshot, what needs to be done.
There's only one active dead list. It's whatever the last snapshot you have as that collects it.
Exactly.
So you're doing this instead of having an active garbage collection?
Right.
Okay.
So it's more like the exact VM. It's an exact, precise collection that only needs to happen at read time.
Well, it only needs to happen actually when you need
Probably
fresh blocks, not at read time, really.
That's actually,
Well, we need
that's
to delete
true.
a snapshot, yeah.
That's true. In principle, we could, when you delete a snapshot, defer handing these things back. And as a matter of fact, we do, in the sense that the task that we execute to go give these blocks back is asynchronous, and it sort of peels them off at a modest clip. And the only reason you never have to wait for it is if you're so low on space that that's the only place you can get more space from.
Yeah.
How do you present the snapshots to the user then, with a parallel file system with links, or how do you go back and pull that stuff out of the snapshot?
Yeah, we'll get to that later, but it's essentially, like NetApp has a .snapshot directory, we have a .zfs directory, and in that is a snapshot subdirectory where you can find all your favorite files from bygone days.
And the only reason we didn't make it the same name as NetApp is because .snapshot sort of, it's kind of like /proc in Linux, right? It's like you can find a bunch of PIDs and also all kinds of other crap that's got nothing to do with processes at all,
Yeah.
right? And so we have under the .zfs directory in the root of each file system, there's a snapshot subdirectory, and there's also a bunch of other subdirectories that one could imagine existing, some of which we're off creating, that describe other things about the file system that are interesting. But we didn't want to put, you know, random other bits of ZFS administrative support into the snapshot directory, because that's just kind of cluttering the namespace up. Okay. Bill's favorite slide.
Well, maybe my second favorite slide. So, .NET end-to-end data integrity, what about that? Well, you know, as clever as we all like to think we are, well, we're not the first people that's, you know, thought, hey, great idea, man, let's like check some of your data, man, it'll be great. You know, people beat us to it by a lifetime or so. But typically what you'll find is you'll have something like this, you know, EMC is famous with their 520 byte sectors, you know, but most of the time you'll find your data, and right next to your data, you'll find the corresponding checksum, which is absolutely great if the failure mode that you're expecting is what we call bit rot. That is a few bits of the data being flipped and no one bothering to tell you about it. Well, as it turns out, with modern disk drives, that's, you know, with the MFM drives, yeah, that was a very, very real method of data corruption. Today with modern disk drives, not so much. They actually have a lot of error correcting codes, Reed Solomon and whatnot on there, because they're pushing the physics of the device so hard that bits can and do flip all the damn time, and they got to be able to compensate for them. And as a matter of fact, they even use that to their advantage, because why use all those bits if they only protect you in an oddball case? So what they do is they take advantage of this by, you know, for example, if you notice the spec sheet of a drive, you can do more random read IOPS than you can write IOPS. And one of the reasons is that when you go to seek the head, they seek it very, very fast and then stop it. And it'll sit there and ring a little bit and settle down. Well, that settling takes time. And they say, well, you know, our checksum foo is so good, we don't have to wait for that ring to stop. We'll get a few bits from one track, a few bits from another track. They'll mostly be from the right track. Our error correcting codes will take care of the rest. And if they don't, we'll just take it up on the next time around, no big deal. And, well, good luck to them. But because of that, you can imagine how much more complex the firmware inside these things are getting. So as a result, you have entirely new modes of failure. For example, a couple of my favorites are, one of them is phantom writes, which is you give the drive a bunch of data and say, here, write this to block 97, please. And it's like, no problem, got you covered, and really just dumps it out.
Here's block 97.
Thank you. Oh, sorry. I caught it. Honest. Yeah, so another common failure mode that you'll see because of the increasing complexity is a misdirected.
I just thought of this now. This is great.
Is a misdirected read and write. It's like
Mr. Disk Drive, may I have the blue block, please?
Sure, no problem. There you go.
Well, I think.
Yeah. Yeah. So you know, you ask the disk drive for. Yeah, that's even better. Thank you.
Yeah, that's sort of the block I wanted.
Yeah. So, you know, you ask the disk drive, hey, can I have block 128? And it's like, yeah, here's block 128. And you ask yourself, gosh, that sounds pretty damned awful. How often could that possibly happen? Well, first of all, there are industry standard terms for it. So it happens often enough that people give it a name. And secondly, any of you that have had the misfortune to debug one of these problems, if you've worked with storage a lot, it's just not a fun way to spend your weekend. But wait, that's not all. So there are all these sorts of failure modes that this doesn't cover, because if you drop the write, well, old checksum matches the old data, no problem there. If you give me another random block, well, that checksum matches whatever random block it is you gave me, yeah, whatever. And also, since in the storage array case, you're doing this data, oh, that picture is gone, but you're doing the checksum down here, it still has a long way to go before it gets up to your friendly little application. And, well, a lot of things could happen. So,
Be ashamed of somebody's data.
yeah,
The way you said that.
yeah, so your data has a long way to go before your application gets a hold of it, and as they say, a lot of things could happen. So compare this to the way we do it in ZFS, and really, checksum your data is not new ideas, but the thing that we did do was we separated the data from the checksum, such that it covers not only a case where a few bits wind up getting flipped, but it covers all these other cases, because since we're a file system, we have to point the data somehow, so we already got to have this tree structure to store the address of the data. So right next to the address, we store the checksum. So since we know where to find your data, we also know what it should taste like when we get a hold of it. So if this data, say, gets a few bits flipped, no problem, checksum detects it. If you give us the old block that used to be there because you dropped the write on us, well, that's not going to match the checksum. If you give us the wrong block, that's not going to match the checksum. Since we're doing the checksum up in server memory, again, something happens along the way, well, we detect it. Driver puts it in the wrong memory buffer, well, we detect that too. Someone besides the file system overwrites it because then you're not updating the entire metadata structure, we'll detect that too. That's all great, you say, but how do I know I can trust that checksum? Simple, because it passed that checksum, and so on and so forth, all the way up to the Uber block. And our security friends call that a self-validating Merkle tree, meaning that the SHA-256 checksum on the Uber block sort of acts as a digital signature of all active blocks in the storage pool. So if anything's wrong anywhere in the entire tree, we catch it.
So what happens in your testing suite when you corrupt the Uber block's checksum independently of the tree?
Yep.
How bad does it look? Since now the whole tree looks bad.
Well, you have to correct all 4 of them.
All 4 of them on every device that was involved in syncing out that transaction group. So it becomes increasingly hard to do that kind of damage.
Right,
But
well, actually, yeah, we're almost, go ahead.
yeah.
I was just curious what, how many red flags come up when you force all of them?
We're 2 slides from Nirvana on this question.
Nerdvana.
That's right. Yeah, so all this is great, but let's see how it actually works in action here. So take the traditional mirroring case. You have an application connected to the file system, connected to the eBone, to the volume manager, and to the disk. Well, mirror is supposed to have both copies on the data, and the annoying thing about that is most people say, oh, mirroring, I'm covered in case something bad happens in one disk. Well, actually, no, you're covered if one disk blows up or tells you very explicitly, sorry, dude, couldn't get the data for you. If the disk drive just gives you the wrong data, mirroring doesn't help you at all. So that's sort of what this happens here is, you would have had 2 green blocks, but hand of God, angry lightning bolt, whatever comes in. You turn the happy green block into the angry red block, and well, now you got a 50-50 chance of having a bad day. So the application says, hey, give me that data back. File system says, I don't know, just where I put that. Ask the volume manager for it, and the volume says, well, okay, fine. Left, right, left. Picks the left side, reads it up. Disk drive didn't tell it anything was wrong, so it's like, okay, good data to me. Passes it up to the file system, and the file system, no error, must be good. And if it's file system metadata, off it'll go in the weeds, doing, well, who knows what. Or if it's not file system metadata, pass it up to the application, who will go off into the weeds, doing who knows what. And the most annoying thing about this is that not only does your data suck, but there was a good block sitting right there this whole time, if only you had chosen wisely.
Does that mean that every time you do a read of a block, however many steps down the tree, that's how many checksums you need to do before
Yes.
the operating system hands that block to the application?
Right.
In the absence of caching, yes.
Right.
Yep.
Yep. And so now let's see how this works in ZFS. Well, we can get angry red blocks like the rest of the world, and the application can ask for them too, and we can get unlucky and pick the wrong side. But the fundamental difference is we don't trust the damn thing the disk drive says to us. So we get that block back, and we do our checks, and we're like, aha, it's not the block I'm looking for. But we know, since we incorporate what's that?
These are not the droids you're looking for.
That's right.
Yes. And because it's a mirror, we know that there's another place we go look for that block. So we read it off the other side of the mirror, checksum it, it's like, aha, you are the block we're looking for. So now we can return known good data to the application, whoever asked for it, And while we're at it, since we saw this angry red block here that nobody likes, we can repair him on the fly, and that's what we call a self-healing data. So anytime we notice an error and recover the proper data, we go fix it in place on the fly, yes.
2 questions. Can the application ask for partial known bad data in the Pessimal case?
Not currently.
Not currently, but you've thought about that,
We have thought
obviously.
about it, and it's
Yeah,
actually,
right.
and it's been requested.
Yeah, there has to be an interface for it, blah, 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 blah.
Yeah.
Second, have you thought about hooking in the repair mechanism, and if it doesn't repair correctly, you start getting health data out another interface saying the drive's going wacky?
That is something that we do with something in Solaris called FMA, a fault management architecture. So anytime we notice this or any other sort of strange event happening, we log it with what we call our diagnosis engine, which has a systemic view. It sees not only individual disk errors, but errors across the entire system. And what it
So
can
you're throwing
do,
it into a pre-existing Solaris system and not doing it yourself.
exactly.
Okay.
And so we can actually say, you know what? All the disk drives on that PCI bus are giving us these errors. I'm guessing 100 disk drives aren't bad. I'm guessing it's that PCI bus. You know, take it from there.
And
Find
what-
another path, whatever.
And one of the things we actually do to verify that this works the way we expect it to is we'll create a, say, copy of the kernel source code and fire off a build in a mirrored file system. And then just scribble random crap all over one side of the mirror. And then watch what happens as the build progresses. And invariably, the build runs all the way to completion, all the binaries that it generates are correct, and you'll see these thousands of checksum errors that have been detected, and they've all gone off and been corrected. And you can find out through like ZFS status, it will tell you exactly how many errors there have been, and FMA will know that this device, from its point of view, is not behaving correctly. So you got all kinds of good data about the fact that something amiss
That's right.
is going on.
Yeah, the diagnosis engine isn't so good that it tells you it's that dork running DD against the raw device, but we figure that's not a common failure.
So mirroring is easy. What about RAID? Well, RAID, it turns out, is actually, in several ways, a much harder problem. And the reason is that in the case of mirroring, all you do is you have 2 or more copies of the data. But in the case of RAID, it's trickier. So the rule for RAID is that you have across any, you have several disks, and across any stripe, whether it's either RAID 4 or RAID 5. And by the way, so for anyone who hasn't paid attention to this lately, RAID 4, RAID 5, the only distinction is that in RAID 4, all the parity is in one column, like it's the green disk on that slide. And in RAID 5, the parity rotates so that you don't have all the parity traffic going to one drive. But conceptually, it's still the same algorithm. And that algorithm is that from RAID's point of view, there aren't really data at parity disks. There's just some number of disks, all of which XOR to 0. And because XOR is commutative and associative and all those good things, if any one disk fails, you can reconstruct that missing disk from all the other ones by XORing them together. And this works great if the way you update your data is by doing what are called full stripe writes. So in this example here, we have 4 drives plus parity. So if you were to write, say, 2K, that would be a 512-byte sector of data on each drive, and then a 512-byte sector of parity, and that will XOR 0 in your RAID. What happens, though, when you want to modify one sector? Well, that's called a partial stripe write, and it makes RAID really kind of a mess, because there's a problem called the write hole, which is, picture, if you will, you want to modify this disk, because there's one sector you want to change. Well, conceptually, you have to atomically modify both this disk and the associated parity. But in fact, because they're separate drives, there's no way to atomically write 2 places at the same time. So if you were to write to this drive and then lose power before writing to that one, then all these disks would XOR not to 0.
The
but
whole
to
stripe XOR.
the whole stripe would XOR to some piece of random garbage. Now, the worst thing about this is that even if this happens to you, you don't necessarily notice it, because after the power failure, you come back up, and if all the disks are still working, you read the part that has the data. You're not having to look at the parity, so you don't notice. But then, say, this disk fails, and you find yourself needing to reconstruct data from parity, and instead of XORing to the right thing, it XORs to random garbage, and you start getting corruption. So this is a sufficiently nasty problem that up until now, there's actually been no way to work around it in software that's sort of cost-effective. In software RAID solutions, it basically relied on having journaling information about which parts of the RAID stripe you're updating, and then you update it, and then you clear the journal. And basically what that means is that every time you want to do a write in a partial stripe write in software RAID, it means that there's a log write, well actually there's a read of the old data and old parity to figure out what they contain, so you can XOR those together, XOR in the new data. There's a write that you have to wait for to indicate that there's a change about to take place. Then you write the new things, and then you clear the log indicating that change has taken place. So you have several back-to-back dependent IOs, and the performance is weeks. So in practice, software RAID has died in the marketplace. And the solution to this problem, losing power is so hard that we just declare it to be a non-problem. You just throw money at it and say, fine, we're going to have NVRAM so that you never actually lose power, you don't have unexpected outages. So that, and this actually solves for you two problems associated with the write hole. One is that it fixes the correctness problem in the sense that because you're not losing power, any changes that you've committed will actually make it out to disk, so the stripes will be intact. The other thing that an NVRAM cache does for you is it can hide from you some of the latency. So if you say, I want to write just to this one sector, you don't have to sit there and wait for the read of old data and old parity, and then XOR your data, and then kick off the write. You can just write asynchronously, it goes into the NVRAM, and then at the array's leisure, it will take that data and write it out to the drives. The downside to this, of course, is that it's expensive.
And we've done this before. Can you say NFS?
Yeah, processor. Yes, and the worst part about this is that this all works great when the drive is nice enough to tell you, hey, I'm dead, or just doesn't answer your question. If you have silent data corruption,